For the first 300,000 years, our universe was a hot, dense ocean of protons, electrons, and photons. This ocean was a plasma so thick and the particles so close together that a photon could only travel a short distance before running into one of the closely packed particles, scattering it in different directions. Because a photon could not travel very far without hitting something else, the universe was opaque. In the very early days of the universe, photons were imprisoned by the crowd of seething particles. As time passed, the universe expanded, creating more space between the jostling protons and electrons. Then, something extraordinary happened. After 300,000 years, the cosmos freed the photons. The particles of the early universe had spread enough that a photon could run unhindered and finally escape its prison. As photons were released from their bonds and became decoupled from matter, the event became immortalized in a snapshot of the cosmos when it was just a baby. These released photons became forever imprinted in the cosmic microwave background. This event is known as recombination, and with it, the universe had just entered the era known as the Dark Ages. At this time, the universe was almost utterly dark and consisted only of protons, electrons, photons, and dark matter. Under the gravitational influence of dark matter and sculpted by its inhomogeneities, dark matter halos formed, gathering the protons and electrons together, becoming an incubator, and giving birth to the first atoms of neutral hydrogen. These newly formed atoms collected under their own gravity along wispy filaments, which grew with the cosmos. The inhomogeneities also grew, leaving behind some regions with an overdensity of atoms, and others much less. The overdense regions collapsed under their own weight and became filamentary, while the underdense regions continued to expand. In a few 100 million years, these primordial atoms will end up as fuel for stars. During the Dark Ages, there was no light beyond the fading background. The early photons of the universe had been released, and in the first few million years after the Big Bang, the universe was primarily neutral hydrogen, collecting in dark filaments under their own gravity. The universe during this period in its history was dark and full of relatively hot hydrogen gas. Most astronomers believe that the first discrete sources of light in the universe came from stars. But for stars to form, tenuous bands of hot filamentary hydrogen is not enough. To make a star, the density along these infant filaments would need to increase by 24 orders of magnitude. At this age, about 10 million years after recombination, the universe is still too hot. We need things to cool. A lot. If the first stars are to form, then something more substantial than very light gas is required. And since the entire universe consists only of neutral hydrogen, the prime candidate is molecular hydrogen. So we wait. The universe continues to expand and cool until finally, after 12 million years, some of the neutral hydrogen has finally combined to make molecules. There isn't a lot at this point, but there is enough. These molecules cool the light tenuous gases enough that molecular hydrogen will be the building blocks of all that follows. The first stars ever to shine in the universe formed about 100 million years after the Big Bang and are very special stars. They are hot, short-lived, and massive. Ranging in size from 100 to 400 times the mass of our Sun, they shine with a ferocity unrivaled in the history of the universe, and for a relatively short time compared to the stars of today. Their size, high temperatures, and luminosity are governed by the physics of molecular hydrogen. Spewing out 10 to the 50 photons every second, our Sun pales in comparison. They burn fuel so fast, their luminosities and energy output can only be supported for 2 to 3 million years. We owe our existence to this cauldron of early star formation. This is the forge from which the universe begins to enrich in heavier elements, including oxygen, nitrogen, carbon, and iron, the stuff from which we are made. At the end of their lives, only a few million years after they were born, these stars are burning so hot and fusing hydrogen so rapidly that their deaths are just as extraordinary as their lives. Depending on their size, these stars will die in spectacular ways, and it is from their deaths that we will be able to see them. Some of the brightest sources of light from this period in the history of the universe come from the deaths of the first stars. The majority, those less than 140 solar masses, will become black holes. The collapse of a core of a massive star, having lost its hydrogen envelope to a black hole, leaves little behind. These stars won't contribute much to future generations. The only thing we will see is the tombstone of high-energy jets and an accretion disk of infalling material, betraying the star's grave. If a star is a little more massive, between 140 and 280 solar masses, instead of a black hole, the collapse will turn into what is known as a pair instability supernova. The first stars are so hot that they form electron-positron pairs, which robs a large amount of energy from the star, causing it to burn even hotter to maintain equilibrium. This creates even more electron-positron pairs, and the whole star explodes. These massive outbursts are so bright, they will outshine all stars in the universe combined. The first stars of the universe were the earliest discrete sources of light that heralded the end of the Dark Ages. They transformed the light elements formed in the Big Bang into heavier ones, ultimately making life and us possible. The Webb Space Telescope will offer us our first glimpse into this crucial time. With its unparalleled detectors and optics, we will, for the first time, have observations of the first stars and the galaxies that incubated them. We will have looked back at our ultimate progenitor and directly into the face of creation.